understand where this formula comes from. But ultimately, okay, maybe I will draw a picture. X, y equal to f of x. F of x is some kind of a curve. You've got a point, say, x0, and then a point x0 plus h. And you take 2 points on the curve, point of x0, point of x0 plus h. You join those two yolks up. Actually, we could even just go from here without talking too much. Anyway, so if you study this thing, this is f of x plus h minus f of x, the change in f, and this thing is equal to h. And actually the way I did it, it's just a little x0. But anyway, so this line connecting these 2 points in the curve, you see, you know everything about the curve because you have the y coordinate in terms of x. So there's a specific x value and a specific h, which you can think of as a step size, I think. You can take the 2 points on the curve, and if you join these 2 points in the curve, which you know about, that black line joining them is called a secant line. And the secant line, I won't draw it because the thing will get, well, we'll show you that. The secant line has a slope that is similar to that of the tangent. I think we spoke about tangents. Yeah, we did. We actually probably drew this thing earlier. But anyway, so this is the tangent, and this secant line, the slope of the secant line, which is f of x0 plus h minus the rise over run, basically approximates the slope of the tangent. Now, how you make this approximation more accurate is you make the h to be smaller, and that's what this h is. Now, what we'll kind of say is that ultimately you can approximate the slope, in other words, approximate the derivative by doing this with a small h that isn't, like the limit h goes to 0, that's a complicated thing that I don't have to get into in this module. But what you can do is just take a small h and you have a good approximation. So what we can say is, take this is approximately, now what we're going to say is, we're just going to say h small. We're not saying that h is necessarily, it's not going to 0, it's just something small. Think of it like a step size. So, like, and obviously the other thing is, the better the smaller the step size, the smaller the h, the more accurate this approximation is. So we have f of x plus h minus f of x divided by h. Now what I want you to focus on at the moment is not the precise thing about that. It's just a change in f, which I'll write as delta f, divided by a change in x. And the thing about this really is the formula that you need, to be honest, rather than using the formulas down the bottom, which is probably where most of us will go. But actually, I'm going to have a change this year. I'm going to say, no, you should look at a change in f over a change in x. And what that will allow us to do is, it allows us to do a few things, which we might see down the bottom here. So, for example, take a 10-meter rod, cut into pieces. Now it's saying a step size of 2. Where should we go for that? Now, imagine this keeps on going. Now, 2 is too large a step size, but everything I think we'll be doing in this chapter will be done with large step sizes. We won't implement fully in VBA, but if you need to actually do any of these things, you'll understand that you need to use a smaller step size. So we'll write down, let's keep the step size of 2. Now the delta x is just another way of writing h. Arguably, well, look, there it is, delta x, h. The idea might be h is something that's going to go to 0, and delta x is, you're happy enough with it just being small. We'll find it. Okay. So we're going to take the temperature at different points. So say this is temperature at point I, and the temperature at I plus 1, and the temperature at I minus 1. And there's going to be a step size the whole time between these of 2. Now what you can do is there's different derivatives you can do. Approximations of the derivative. Now, I won't argue why all these are, now, are they equally valid? No. But there's different things you can do. So one thing is you can look from here to here and consider, like, this is the point you're interested in, this is your H. And then you can do over this region, the derivative is approximately the change in F over the change in X. That's called the forward difference. We'll be using that. The other one you could do is, you could do the backwards one. Now this will correspond in the limit. So H going to 0, that actually includes H coming to 0 from the positive side and H coming to 0 from the negative side. So like if you're trying to do this thing properly, we always draw it forwards, the H being positive, but it can also come from the other direction. And that would be the backwards one. We'll do that as well. And the other thing you can do is you can average the two of them out, and that's called the central finite difference approximation. And essentially, center it here, you can look at the change in F from here to here, divided by the change in X. And these are all approximations that we can use at different points in this thing. Right, so now it says F of X here, but actually all the things we'll be doing will be derivatives. So let's write some down. So the derivative, and usually actually we'll be doing this with partial derivatives, but don't worry about that. So the first one we'll do is the forward. And the other thing is, okay, these derivatives are evaluated at different points. So all of this is evaluated at, now I've got the temperatures there, and I've written them as temperature I plus 1, temperature I minus 1, and these correspond to X coordinates, say xi plus 1, I minus 1. So this is the derivative at xi, at the midpoint. And actually what we're going to be doing is we're going to be approximating a differential equation at various different points, is what we're going to get. Okay, so this derivative is approximately. So the first one is the forward one. So between these two, what is the change in the function? Well, it's ti plus 1 minus ti. Now what I'm going to do is, rather than writing down 2, I'm actually going to write down delta x. So that's the change in the function divided by the change in x is delta x. So I think it's written up there, right here, take delta x to be, in this specific example, is 2. So that is how that's the forward difference approximation of the derivative at this point. So this is forward finite difference. Okay. We can also do the backwards one, which is over this region. So I'm not going to say, now this, I could write approximate again, but I'm just going to write a comma instead. Like, or you can use the backwards one. So the backwards one says the change in function is this minus this. And the change in x is the same, it's delta x. And this is the backward forward difference. As far as I know, you did do this with Bob. And then the last one is you do, so there's two ways of thinking about this. You do, okay, change in f over change in x over this period, or you say, oh, I'll average these two out. And if you do that, you get the same thing in both cases. It is a formula that I will give to you. So if you're going over this region, the change in f is ti plus 1 minus ti minus 1, and you're going, the change in x is 2 delta x. And this is called the central forward difference. Now, I don't have all the formulas written down here, but this one here corresponds to the forward difference. So the value of the function at the next point minus the value of the function at the current point divided by the difference. So this here is the forward difference. Finite difference. The finite difference says you're not doing the limit as h goes to 0. You're keeping the difference finite. Okay. And then you got a formula for the second derivative. It's down there. It'll be given to you. So basically, the second derivative is the derivative of the first derivative. So instead of f's here, you have f dashes. And then you approximate this. This is using the forward difference from here, say. And this is the previous point. So you're going forward from here, and you end up with this formula down here. So this is like the language here would be, or the way of thinking about this is like the next, because it's plus 1 minus twice the current, sorry, this should be equals current value of the function loss previous, and it's divided by, say, the step size squared. So these approximations we are going to use. Basically, we're going to derive partial differential equations that have derivatives in them and second derivatives, and we're going to cut up the thing. So, for example, if this is a rod, we'll cut up the rod into loads of pieces. We'll look at the temperature at each point, and then we've got the differential equation. We'll approximate the derivatives using these finite differences at each of the points, and what you'll end up with is loads of equations in the temperatures at the points, which will be linear equations. And we can attack that, however. So this is actually strictly revision. All those formulas will not have to be remembered, but I think the best probably thing here is the thing up the top. Basically, the derivative is approximately whatever you want to do, changing f over changing x. If you want to make it exact, you need to do the change in x going to 0.